Today we're going to begin talking about problems that involve more than one force. Up until now it's been one force, the applied force, the force of friction, whatever the case may be. We're going to start talking about problems now that involve the applied force and the force of friction and some other forces potentially as well. But before we do that, we have to define something, a new term, that's going to help us to solve these problems. We're going to define what we call a free body diagram. A free body diagram, sometimes abbreviated FBD. A free body diagram is a diagram that shows all of the forces acting on an object. All of the forces acting on an object. Now, sometimes we also label other things because we have to write down givens, and sometimes it's just convenient to label it right on the diagram. But the free body diagram doesn't require other things. It requires us to draw and label all of the forces that are acting on an object. So let's say, for instance, that we've got a box that's on a flat horizontal surface like this. Let's say that that box is being pushed to the right by Jacob with a force of 500 newtons. And let's say it's being pushed to the left by Nick with a force of 600 newtons. So Jacob to the right with 500, Nick to the left with 600. We want to draw both of those forces acting on this. Jake to the right, we'll call that Fj, although you could really call it whatever you want, F1, Fa, Fj, whatever you want, right? Label it 500 newtons to the right. Nick was pushing it to the left with a force of 600 newtons. Now, watch what I'm going to do here, guys. I could draw that this way, like this, or I could draw it over here, or I could draw it right here. What's important here is two things. One, that I draw it in the right direction. I'm drawing it to the left. And two, that I draw it the right length, more or less. This one should be slightly longer than Jake's force. How come? Because it's a bigger value, right? It's 600 newtons. So it should be about 20% longer. Where I draw it doesn't really matter. As long as I get the direction drawn right, and as long as I get the ballpark magnitude drawn right, then it doesn't really matter where I draw it. Is that it? Is my free body diagram done? Have I drawn all of the forces acting on this box? Nope. We're missing something here. Yep, Haley? Sorry? Yeah, we got gravity acting down on this, right? Now, we don't know how gravity compares to Fn and Fj. Actually, let's not call this Fn. Okay, you're going to see why I don't want to call it Fn here right now. Let's call it, Nick, we're going to pretend, Nick, what's your middle name? What's your middle name? Yeah. Glenn? Yeah. Okay, oh no. Well, what? I don't want to call it FG either. That's gonna mess us up later on as well. Let's just call it FA. Let's call it FA. Okay. FA. Okay. All right. So somebody told me. Who told me about gravity? Who was that told me about? Okay. Gravity's acting down. We don't know how that value of gravity compares to the applied force by Nick. We don't know how that force of gravity applies to the force by Jacob. So we can't really draw that the proper length because we don't know its value. But if we get the direction correct, that's good enough. Now, could we have drawn that force of gravity somewhere else? Like maybe up here? Could we have done that? Sure we could have. As long as it's drawn in the right direction, which is downward here. Now, is there any more forces acting here, or is that it? Yep. Good, there's a normal force. If these three forces were the only forces acting, what would happen to this object? It would go down, and it would also go to the left. It would kind of go down this way somewhere, right? We have a force to the left that's bigger than the force to the right. That's a net force to the left, which means it's going to go to the left. But we also have a net force that's downward, so we're going to find that it's going to end up going somewhere between left and down. Now, that doesn't happen, right? We're on a surface, so that doesn't happen. Oops, that's not what I want to do. There we go. That's what I want to do. We know, as Venture said, that we have a normal force acting up. Now, we don't know how big the normal force is, or do we? Tell me when to stop drawing the normal force. Yeah, that's the normal force, right? We don't know its value, but we do know the normal force is going to be equal to the force of gravity in this situation, right? Not always. Okay, if I happen to be on a surface like this, and you've got an object on the hill like this, let's say it's being pulled up the hill with a force of 20 newtons. Then we would say FA, F whatever, is equal to 20 newtons up the hill. There's a force of gravity acting down like this, and there's a normal force acting up at 90 degrees. Fn would not be equal to Fg necessarily in that case, right? Until we do calculations in this case, though, we wouldn't be able to determine exactly how big it was. We just know that it's not necessarily exactly equal to gravity. That make sense? So a free body diagram shows all of the forces acting on an object. Maybe I show a velocity as well. Maybe I know the mass of this. Maybe the mass is 2.0 kilograms, and I label the mass. But that's not technically part of the free body diagram. That's just sometimes something that I do because, hey, I got to write down my givens in the problem anyways. Maybe it makes sense just to throw them onto the diagram. Make sure, though, that you have all the forces acting on it. That becomes really, really important next week when we go to solve these multi-force problems for the acceleration or for some other variable. There's an example that we see up on the board right now. It says a car with a weight or a force of gravity of 10,000 newtons downwards is coasting on a level road. The car experiences a normal force of 10,000 up. They didn't need to tell us that. We knew that, right? If it's coasting on a level road, we know that gravity is equal to the normal force. There's a force of air resistance of 2,500 newtons backwards and a force of friction exerted by the road on the tires of 500 newtons backward. Draw a free body diagram for this situation. Here's my car. By the way, when we draw these diagrams, they don't have to be good in terms of, artistic. I don't even have to draw wheels on my bloody car, for heaven's sake. Like, I can make it a block or a circle. All I need to do is make sure that I have an object labeled there. Now, I want to label the force of gravity acting downwards of 10,000 newtons. I'm going to label the normal force acting upwards with 10,000 newtons. I can draw it right here. Or I could have drawn it up above the car. It doesn't really matter, as long as I draw it the same length as gravity and as long as I draw it in the right direction, which is upwards. What else do I got here? I got air resistance. Which way is air resistance, left or right? Yeah. Yeah. If we assume that it's moving to the right, then air resistance will act to the left. Can you tell me when to stop drawing the force of air resistance, please? Okay, I'm drawing air resistance right now. Tell me when to stop drawing it. Right there? Probably should be a little bit shorter, actually. How long should it be compared to this force of gravity? Should be a quarter of the length, right? It doesn't have to be perfect. You don't have to measure it. Let's try to get it somewhere in that range of a quarter of the length of force of gravity and the normal force. Let's label that now. F air, they tell me, is 2,500 newtons. Now, the force of friction between the road and the tires is 500 newtons backwards. Look, it's getting a little cluttered over there on the left-hand side, so I'm going to draw the force of friction on the right-hand side. Can I do that? Yes, Jacob? Yeah, I can draw wherever I want, right? But I have to draw in the right direction. Which way is it acting? It's acting to the left still, right? Even if I draw it on the right-hand side, it's still acting to the left. Now that should be a really short force, right? 500 newtons, like this. Now it probably should even be shorter than that, but I'm going to draw it that long so at least that I can see it, so I can distinguish between that and a dot. Does that make sense? This isn't crazy hard, right? Next week, what we're going to do is learn to analyze these problems. And it's not going to be that hard. Okay? At least the basic examples of them isn't going to be that hard. You're going to find that, in this case at least, the force of gravity and the normal force cancel. So they become irrelevant because they don't contribute to motion because they cancel out, right? And the other two forces don't cancel. So what we're going to do is find the net force. What is the net force on this? What is the unbalanced force, the sum of the forces, the total force? Max, was your hand going there? No? Can you tell me what the total force is there? Keeping in mind that Fg and Fn cancel each other out. So they matter, but they don't contribute to the motion. Yeah, it would be 3,000. Good. So the net force would be 3,000 newtons. And then we would set that net force of 3,000 newtons equal to mass times acceleration, m times a, and we could solve for the acceleration. Does that make sense? We'll spend some more time on that next week. What I want you to do right now is to take a look at the questions, the two questions on page 131 that simply ask you to draw free body diagrams for situations. So practice those free body diagrams, and then we'll deal with what we're going to do with those free body diagrams. So look at the first one. Driver sees a pedestrian, steps on the brakes. There's a force of air resistance of 2,500 newtons. Okay, so let's assume he's moving to the right. The force of air resistance would be 2,500 newtons to the left. The brakes engaged, there's a force of friction of 5,000 newtons backwards. So we're going to draw that twice as long. We'll call that FF, is 5,000 newtons. And I think our force of gravity was 10,000 newtons, right? So that's going to be twice as long as that one. So our force of gravity is going to be 10,000 newtons. Is that good? Are we done? Are we done? What's wrong with this? What am I missing? Yep. The normal force, which is going to be the same as the force of gravity, but opposite direction. It's also 10,000 newtons. Good? Let's take a look at the second one now. Number 2 says a car moving at a constant velocity starts to speed up. The weight of the car is 12,000 newtons down. What's that weight correspond to? Remember, we defined mass as the amount of matter that something possesses. Weight is defined as what?
Gravity.
Force of gravity acting down. So we're going to say Fg is 12,000 newtons down. There's a force of air resistance of 3,600 newtons. Let's assume it moves to the right. Air resistance will be 3,600 newtons to the left. And it's going to be, I don't know, about a third as big as the force of gravity. We'll call that F air is 3,600 newtons to the right. Now, could I have drawn that on the right-hand side if I had wanted to? Sure, I could have, as long as I draw it pointing to the left, right? The engine engaged, the force of friction exerted by the road on the tires is 7,200 newtons forward. So it's that force that actually propels the car forward. Ironically, friction, the resistive force, pushes the car forward. Now, I can draw that wherever I want. Doesn't really matter. As long as I draw it about twice as long as the force of air resistance and a little bit shorter than the force of gravity. So we're going to say the force of friction is 7,200 newtons forward. Right? Good? All done for the weekend or for the week? Nope. What's wrong? What are we missing?
Normal.
We're missing the normal force. It didn't tell us about the normal force, but we know there is a normal force, and it's acting upward with a value of 12,000 newtons. Good? All right, now we're done for the week.